So it's my great pleasure to introduce Jim Kurose, who will be our speaker. Jim is the Assistant Director at the National Science Foundation for the CISE Directorate. It has an annual budget of about $900 million. And within that budget is the money that funds the Blue Waters Project, the Exceed Project, other things as well. He also serves as the co-chair of the NITRD Subcommittee on National Science and Technology for the National Science and Technology Council. And I believe has been at NSF for about a year plus a little bit, year and a half. He comes to us from the University of Massachusetts at Amherst, where he is a distinguished professor of computer science and also served a number of positions, leadership positions there, including interim dean and department head of computer science. The other thing that he has done is help form the Green, the Green Massachusetts Green High Performance Computing Center, which is a combination of computing for all the state institutions and universities there. So he understands what it takes to put a big facility together and operate that as well. I won't go into all his national awards and things, but he also was 8 times the Best Teacher Award, if I understand correctly. So I'd like to invite him up and share his thoughts with us.
So thank you very much. I'm really very happy to be here, and I'm really sorry actually that I can't stay for the whole meeting. So Tuesday is like all meeting day at NSF, and so I need to head back to the East Coast. But I wanted to spend some time here and come visit with people yesterday and today, just because the work that goes on here is so important. And as Ed mentioned, Blue Waters is the only Track 1 leadership capability, computational capability that we have in the United States for all of science and engineering. And so the work that goes on here is not just at the cutting edge. You folks are really defining the cutting edge of your fields and using Blue Waters as the vehicle to do that. So really the eyes of your community and the eyes of lots of people around the country are on the kinds of activities that are happening here at this meeting. So I'm really very happy to be able to be here and spend some time and learn more about what's going on here. I give talks a lot, say, to the National Science Board, and one of the things they always want to hear about is what's going on with cyber infrastructure. So I've been at NSF a year and a half, and that's probably 6 or 7, maybe 6 National Science Board meetings, and I think in all but one of those, I've spoke about what's been going on in cyber infrastructure, and in a couple of cases in Blue Waters, in particular to the Science Board, because the National Science Board also cares very deeply about this community and what's happening in this community. So I'm very happy to be here. I got to spend some time with the fellows at breakfast, so congratulations to all of you graduate fellows and those of you who are undergrads here and doing poster presentations. Congrats to all of you here. And I wanted to join Ed Walker in thanking the Blue Waters team, the leadership of the team, and the entire team for the amazing job that they've been doing here. It's really a national treasure, and we're all of us in the science community are incredibly fortunate to have such a great group of people leading this. The NSF is really unique among the agencies in that we work so closely with all of the researchers in the science domain. So it's not sort of like DARPA where things are sort of targeted and come from a high and this is the way it's going to go. We at NSF work really incredibly closely with the science community, workshops and panels and understanding what it is that the science community needs. And it's this close interaction between NSF, leadership of folks like here in Blue Waters that really makes science and engineering in this country go. So thank you, Bill, and to the whole Blue Waters team for everything that you're doing. Okay, so I guess with that as preface, here's what I'd like to talk about. I want to, some of you will have seen some of this before, but I did want to just start off with a couple of brief words about the National Science Foundation and the CISE Directorate. I want to spend some time talking about research cyber infrastructure really writ in the large. So not just, yes, we'll be talking about Blue Waters, but also really talking about the whole cyber infrastructure ecosystem here in the United States. There have been a couple of really interesting activities and announcements made over the last year. The National Strategic Computing Initiative, I want to talk a little bit about that, and NSF's Big Ideas, which the director of NSF discussed with the Science Board, National Science Board, just about a month ago, and then I'll summarize. As Bill mentioned, I've been at the NSF for about a year and a half. I've been a professor for 32 years before that, so I feel like I'm much more a professor than an NSFer, at least time-wise, that's certainly true. So you all know, almost all of you are academics, the worst thing that can happen is you get up and you start talking and talk, and everybody's just like falling asleep. So if you have comments or questions, I'm going to try and stop and make sure that we have some time for some dialogue, both during and at the end also. Okay. So when you ask somebody, a random person in the street, well, or maybe in a university, what does the National Science Foundation do? Everybody knows that the goal of the National Science Foundation is to promote the progress of science, right? But in the Organic Act, it's also the case that our call is to also advance the national health, prosperity, and welfare, and also to secure the national defense. And when you think about computation and you think about cyber infrastructure, yes, not only does cyber infrastructure power a lot of the discoveries in science and engineering, but it's also critical in promoting national health, prosperity, and welfare, and also in securing the national defense. So the kind of stuff that we're doing here, yes, absolutely basic research, that's what we're going to be talking about, but there are other aspects of the NSF's mission as well where computation and cyber infrastructure are critical. So this little infographic just gives you a little bit of background about the National Science Foundation as a whole. Our budget request for 2017 is just shy $7.96 billion. We get about 50,000 proposals a year, about 11,000 of those are awarded, and in the end, as you all know, the most important thing, the people, around 300,000, this is across all of the investments being made by the foundation, 300,000 NSF-supported researchers in all areas of science and STEM education as well. So I once gave a talk not too long ago where someone invited me to talk and they said, just one requirement, no org charts. So I apologize for this, but otherwise it just would have been a bulleted list, right? Of, here are the 7 science directorates, but here are the 7 science directorates. And I think actually one of the amazing things about Blue Waters and also the use of cyber infrastructure is that there are folks from that have a home in all of these directorates that are represented here. And that's really one of the really amazing things about how the footprint of computation and computational science is just really permeating all areas of science and engineering. So what we do in CISE, what happens in computational science is obviously critical to all of these directorates across the foundation. I'd like to say that was my last org chart, but I actually have one more I want to show you in just a second. So actually, I started out, I have an undergraduate degree in physics. When I was meeting with the students this morning, I was thinking way before they were all born, I started writing code to do simulations of electron capture with accelerated proton beams and alkaline earth metal vapors, right? And I thought, wow, here are these students that are doing computation, and we didn't have anything obviously like Blue Waters back then. And then I got interested in computer science, and I don't know, why do you get interested in things? Because they're just so intellectually stimulating. And then sort of fast forward and you look at what's happening nationally in computer science, in computational science, and I feel a little bit like Forrest Gump, right? Because you're just like, whoa, look what's going on here. So what I'm showing here on this slide is, the White House through the Office of Science and Technology Policy has national initiatives, right? This is the president and science leadership in the United States, science and engineering leadership standing up and saying, hey, look, these are areas where they're so important that we need an all-of-government approach. Often there's additional funding that comes along with this, and these are declared national priorities in science and engineering. And so a year ago, as of the beginning of last summer, that we had a national initiative in big data. We had one in the National Robotics Initiative, which is now, actually just last week, celebrated the beginning of its 5th year with a really nice Hill event, and then the BRAIN Initiative. And within the last year, it's been really interesting to me, the president announced the National Strategic Computing Initiative last July. I know Ed Seidel and I and another number of others were there for that particular launch. The Smart Cities Initiative in September, and then this past January, a computer science education initiative called Computer Science for All. And so, I don't know, I feel like Forrest Gump because, you know, you look around and say, wow, look at all of these areas in which computer and computational science is so important for the country. We're really just sitting at the center of so many exciting things going on. And when you look at those, I'll argue maybe not for computer science education, but cyber infrastructure and the kind of work that goes on here impacts 5 of those 6 national initiatives. Okay, last org chart, I promise. So this is just so that you understand what the CISE Directorate looks like, and this is probably the directorate that many of you here are most familiar with. So this is where Ed has a home. The Division of Advanced Cyber Infrastructure, ACI, Irene Qualters, who many of you know, and I know she's been here for this symposium before. And you know, one of the things that I will be talking about is when we think about advanced cyber infrastructure, and this was really clear in what Bill Kramer was saying just a little while ago. We're not just talking about cycles, right? We're talking about data. Yes, we're talking about high performance computing. We're talking about the networking that goes on. We're talking about software, and we're talking about the people, and we're talking about the sustainability of those kinds of all of those pieces of the ecosystem. So ACI is one of the 4 divisions within the CISE Directorate. We have the Division of Computing and Communications Foundations, and that's actually where software and hardware foundations are. So the research side of things, before we start talking about actual cyber infrastructure, goes on there, and I know a number of folks here are probably funded through that program. We have computer and network systems where operating systems, cloud, networking lies, and then finally our division for information and intelligence systems. This is where AI, machine learning, robotics, data mining, big data is. Okay, so I promise that is my last org chart. Oops, sorry. I should mention we have 2 science advisors also in the front office in CISE, and just to give you an idea, of the importance of these areas to us, we have a senior advisor for research cyber infrastructure, Peter Arsberger, and a senior advisor for data science, Chaitan Baru. Interestingly, they both come to us from UCSD, which is nice. Okay, so the CISE by the numbers. Our budget submission for 2017 is just under $1 billion. It's $933 million for the fiscal 2015 year that we ended. The success rate shown there in that orange circle, 23%. So it used to be higher. It's I'll talk about budgets in a second, and then I'll move on to maybe more interesting things. But that is not counting workshops. It's not counting eagers and things where proposals that are generally funded, or almost, well, not invited, but funded at very high rates. So that's across the directorate as a whole. We do make our career in the career program for early investigators. The success rates are actually quite a bit higher than that in some of the divisions. We talked about the importance of graduate students and also early career faculty for the discipline as a whole, and we feel it's very important to be investing there. And then just again in terms of the people, 7,300 researchers. So those of you who are graduate fellows here, we count you among those 6,400 graduate students, and 2,300 undergraduates, primarily through the REU program. So a lot of people. Okay, I don't know. In the end, money counts just because it's an enabler of doing things. This is just, everybody should know, what are the budget realities in DC? So this is going back to 2010 up through 2017. That bump up shows our request, not the allocation yet. And you can see, the message here is really in the title, that modest sustained growth across all divisions. And you can see ACI in there, and CNS, and IIS, and CCF. And really, for the foundation as a whole, my sense is CISE has done a little bit better than the foundation as a whole, but this is the budget reality of being in DC right now. And well, everybody should know that. Okay, I'd stop and ask for questions, but it was mostly just sort of the big picture stuff, but maybe I'll stop just to say that, as a professor, as a teacher, we're always open for questions or comments, so, and discussion. Anything anybody want to say before we move on to talk about the research cyber infrastructure? Okay. All right, I'm going to let that silence pass, but the next time, next time I'll see if I can really pull some comments. Oh, thank you, Mike.
If not, he's going to give us a quiz, so you better ask him.
No blue books, sorry.
So at a very high level, when the White House announces an initiative like the ones you listed,
Yep.
what happens inside of NSF? In a very short...
Okay, so Mike's question was when the president announces an initiative like that, what happens within NSF? Well, first of all, there's a lot of activity within NSF before the president actually makes that kind of announcement. So there's usually a fact sheet that comes out, and when we make an announcement, there's an announcement of these are the kinds of investments that we're already making in these areas. So for instance, I can remember the Smart Cities initiative since, actually the Computer Science for All. This is for bringing computer science education to high schools across the country, right? So we at NSF had already committed $120 million of funding to do very specific things in that. And so that was sort of highlighted in there. What we hope is that now that this is a national initiative, that there'll be increased investment in those areas. And so sometimes things like big data and the National Robotics Initiative, there is some discretionary funding that can come along with these activities that comes to us through OMB. And so certainly that's the kind of thing that we really hope for and look for, because these are things that really require national investments. And one of the things that I see at NSF is we are doing so many good things. And if we have to double down to make an investment in a new area, we really want that to come with additional, certainly in part with additional funding. And so that's hopefully part and parcel with being a national initiative. Okay. But I should say that the reason, again, that they're national initiatives in the first place is these are areas that are identified as high priority, high impact areas for the country and for science and engineering, right? And that's why we're doing them. Okay, so I want to go on and talk a little bit about cyber research infrastructure. And I mentioned that I have the great fortune to be able to be asked multiple times to talk to the Science Board, National Science Board, for example, about that. And honestly, it's almost an easy thing to do because there are so many amazing things going on. And in the end, we have this cyber research infrastructure to enable science and engineering discoveries. And if you look within CISE and you think about the CNS division, for instance, that folks here probably don't have too much interaction with, but there, we've been making investments in mid-scale research infrastructure for the networking community that has given rise to technologies like software-defined networking. In this community here, the work that Klaus has been doing and others with the HIV capsid on blue waters at NCSA has really, is amazing work. You can't go anywhere and talk about science these days without talking about LIGO. And then the great stuff going on initially in plant and plant genomics, but now being broadened through the work going on in iPlant and Cyverse. And so all of these are great examples of research infrastructure that then gives rise and enables the scientific discoveries. And in the end, sometimes, I don't know when you do this, if you do this when you teach. When I teach, I always hope that people walk away and 3 weeks later, they'll remember 3 things that you said. And so, one of the main bullet points I always hope that folks walk away with is the understanding that we have this research infrastructure to enable discovery. I like to say that success has many parents, and so LIGO has just been a tremendous success, and I've been using this slide for a while. I didn't prepare it for right here, but you see NCSA and SDSC and TAC. I just took this off of all of your. I know Mike and Bill are here. I took it off your home pages, and the important role that computation and computational science has played in the LIGO discoveries and in the modeling and simulation that led up to that as well, I should say. And so I think rightfully so, this community plays a very important, claims a very important piece of the success for the wonderful things that have happened with LIGO. Of course, I'd mentioned the work that Klaus and his notion of, thinking of blue waters as a computational microscope and being able to look at the atomic level structure of the HIV capsid, that protein structure that surrounds the HIV virus. And obviously, he's been working on that with folks at UIUC, at Pitt and Vanderbilt, and really pushing forward the frontiers there. So these are examples of the kinds of science and engineering that you folks are making, and that Blue Waters as a track one leadership capability is enabling. So let's see. I want to just say a little bit about cyber infrastructure, a little bit more broadly writ. So Bill mentioned that ACI, for instance, the Blue Waters program is within ACI. 55% of the ACI budget, which is a little bit north of $200 million a year, goes for production quality research infrastructure like Blue Waters. The other 45% goes to really prototyping some of the more advanced capabilities that we expect to show up broadly in the cyber infrastructure. So you might have heard about the DIBS program or the SI2, Sustained Innovation for Software Infrastructure program. Those come in that other 45%. But 55% of the budget really goes into this kind of production cyber infrastructure that science and engineering needs to do its science. In the other divisions of CISE, only 6% of the budget actually goes for research infrastructure. And that's typical for what we see in engineering. It's more than in some of the other divisions, other directorates, but obviously math and physical sciences and geosciences invest more than 6%. Okay, so I just want to show you this quickly. This is for the CISE community as a whole. I wanted to just say something about network research testbeds, and then I'll move on to cyber infrastructure more broadly writ. So actually starting 10, 15 years ago, actually I chaired the workshop, and this is how things happen at NSF, right? The community says, here's something really important, gets funding for a workshop in something. So in this case, in the early 2000s, we as a research community, my area is computer networking, we knew we needed experimental infrastructure because the internet was was production by then, right? We needed research test beds. NSF responded to that workshop, and in the first round of network research test beds has invested $25 million over 13 years. The Genie project followed about 6 or 7 years ago, an at-scale virtual laboratory for networking experimentation, like Blue Waters. Genie counts the numbers of users and the kinds of things they do, so more than 6,500 users running. These are networking researchers who have a national research infrastructure that they can experiment on and push their science and engineering forward. We have US Ignite, which is pushing gigabits out to the edges and enabling innovation in the application space, and we've been working with a number of different communities around the country in doing that. And then most recently, experimental infrastructure for cloud architectures. This is the NSF Future Cloud, and we have 2 projects there funded, Cloud Lab and Chameleon, that I know a number of people here are invested in. So if you're interested in cloud type of cyber infrastructure and you want to work with folks who are pushing the next generation and APIs and services that would be available for cloud for scientific computing, these are the folks to go to, and I or others here could help make that connection. Okay, so let me talk about cyber infrastructure more broadly writ, and something probably a little bit closer at home for this community. So, if there's really, you folks know this, but when I talk to the science board, this is always the first point that I say. I want to make sure you take this home, that when we talk about cyber infrastructure, it's not just about big iron, right? So yes, absolutely, computational resources are critical, but it's about software, it's about data, it's about the networking, it's about the scientific instruments that are generating the data and attached to that cyber infrastructure. And it's about people, it's about organizations, it's about programs like the Blue Waters Fellows programs and the communities that make up this research community. So when we think about cyber infrastructure, I know I'm sort of bringing coals to Newcastle or preaching to the converted, but it's not just about the hardware, right? And this is a message that I try to carry out from this community very broadly across the country. So I wanted to just walk you through some of the investments that we at NSF have been making in these different areas. So many of you know the CC, it used to be CCDNI, we just call this the Campus Cyber Infrastructure Program now that Kevin Thompson's been leading for quite a while. We now have more than 200 campuses around the country with 10 gigabit and higher connectivity. And so if you think about a national cyber infrastructure, one of the things that you really need, especially when computation and data is distributed, is this high-speed capability. So Bill was talking earlier about the capabilities coming in to UIUC and NCSA and Blue Waters. We need that kind of connectivity across the country for all of our scientists and research scientists and engineers. And that's been one of the goals of the Campus Cyber Infrastructure Program. And you see the places we've been making investments there. We make investments nationally also. So most recently, we lit up a 100 gigabit per second link between Seattle and Tokyo, working with NICT, our colleagues in Japan, and NSF co-funding that. High bandwidth connectivity into the southern hemisphere, particularly for some of the instruments, and over to Asia as well. So at the networking area, we've got the CC Star program and these international connections that provides us the capability of building a distributed global and national cyber infrastructure. Okay, speaking a bit about the computational resources. So these are some of the flagship activities going on in the National Science Foundation and ACI. So you see Blue Waters there as really the sort of the single track one investment, incredibly important that we have. Stampede 2 was just was previously authorized and just announced just about 2 weeks ago down in at UT at TAC. And then we have, so that's sort of the large-scale computation. Mike Norman's here from SCSD, San Diego Supercomputer Center, sorry. And the Comet system was sort of, I know you don't break a bottle of champagne over it, but was sort of opened and christened last September. Wrangler coming on at Texas, and then Bridges at PSC and CMU, and Jetstream at Indiana. Our capabilities coming online more in the cloud. So we have data, sort of more data optimized systems, cloud systems, long tail, high throughput at Comet, and then the large scale computation at Blue Waters and Stampede. So we really have this sort of integrated set of activities because people, there's a range of needs for computation. Okay, I know that Bill Gropp is here somewhere, and he's over there, and I know he's going to be talking about a really important and impactful report that he co-chaired on future directions for advanced cyber infrastructure for supporting U.S. science and engineering in 2017 to 2020. I just want to say a couple of words about that because I know in a second, because I know Bill will say more about that. So the use of this cyber infrastructure is growing. What you're seeing here is a plot of exceed service units that are used by Directorate, and so I will point out, you can't see it, but the y-axis there is log scale, right? Okay, and then you see time from 2005 to 2015, the usage in these exceed service units, and you see that by Directorate. So there's MPS at the top, but one of the amazing things is that we see 2, 3, 4 orders of magnitude increase over a 10-year period in the number of exceed service units that are being used really across all of the directorates. And I once said that, well, look, social behavioral and economic sciences is using as many service units as MPS did 10 years ago, and then so I got my hand slapped because that seemed, well, so okay, so they're where MPS was 10 years ago, but think of where MPS was 10 years ago. So I mean, this is an amazing amount of computation that's now being used in the social behavioral and economic sciences, and as you see, they're really across the board. So I mean, this is just sort of prima facie evidence about how important cyber infrastructure is to all of science and engineering. That's sort of measured in terms of these exceed service units. The number of active institutions participating in XSEED has doubled. The number of PIs per project has tripled. And probably most importantly, because it comes down to people, the number of active users has gone up by a factor of 5 over that time period. And so again, all of this just pointing out the incredible importance of research cyber infrastructure. Many of you folks here use XSEED for as part of your work and go through the XRAC and go through gateways and portals that are supported and part of XSEED. And like Blue Waters, community is very important to the folks in XSEED, so community training and community building. And this notion of having experts who are embedded, the campus champions, for example, domain scientists who can help each other out. We were talking about this with the grad students this morning, right? A lot of times, you just need some help, and some help getting started can just take you a million miles, right? And so the ability to link to domain experts across campus is something that XSEED's doing. We have the ACI ref that Jim Bottoms at Clemson, and I know a number of people here are participating in, is another important activity there. So we're sort of moving up the stack, if you will, talking about not just the underlying physical resources, but now the middleware that helps connect that and the people and the resources. So again, when we think about a research cyber infrastructure, I got this slide from Irene Qualters, we put people at the center of that, right? Because it's all about the science that they want to do, and everything else is in support of that. So I want to show you something that for you folks may be second nature, but I will tell you that talking about how you assemble this into sort of a coherent, integrated reference architecture, you might call it, is really important. It's important because it allows us to communicate what it is we're doing in terms of the cyber infrastructure to people who are outside of our community. And so the idea here is that at the bottom of this, we've got the physical resources that I was talking about. So in yellow there, we've got the national and international research and education network connections. We've got NSF-supported cyber infrastructure. Blue Water is obviously a key piece of that ecosystem. But you folks also have resources on your campus. There are private clouds, and then there are international connections and collaborations that need to be supported. We've got this layer of middleware, if you will, that worries about issues like getting access to the machine, single sign-on, the open software that's being developed there. And then, of course, at the very top, we've got the science that happens, right? So more and more, I think where we're seeing a lot of development really across the board are on gateways and science portals where domain scientists can store and share their workflows with each other, so it's that much easier to be able to build on the research that your colleagues are doing. And so if you sort of go up the protocol stack, the architecture stack here, you'll see increasing diversity, increasing disciplinary emphasis, right? The resources at the bottom are shared. As we go up, we see more and more domain-specific types of things, the workflows that are very specific to plant genomics, for example, in iPlant. And then as we go down, we see that increasing interdisciplinary sharing of the resources at the bottom. And then, of course, across all of these, the importance of government and policy and the issue of sustainability. And I've had a number of conversations with here. This issue of sustainability is just so important. And in some ways, the hardware sustainability is almost the easiest, right? We need to be able to sustain software. We need to be able to sustain people and have that kind of continuity. And that's something that's incredibly important. So anyway, I've in talking with my fellow assistant directors at NSF, this slide has really sort of helped them see sort of this notion of a coherent architectural vision and how the various pieces of activities that ACI and others are working on and that you folks are a part of all sort of assembles into a coherent whole. So that's sort of this is sort of where we are today. If we start looking forward, ACI is also funding sort of the next generation of research cyber infrastructure. So a number of folks here are involved in the data infrastructure building blocks, or the DIBS program. So an example of an award that was made there fairly recently was to Larry Smarr and others at UCSD and actually across the California system on the Pacific Rim platform that really is aimed at enabling big data across lots of different science disciplines and in a distributed way across a number of places in California. Something going on at UIUC is the CyberGIS. This is evolving the GIS software for sustained innovation in geospatial activities. And this is funded under the Software Infrastructure for Sustained Innovation, SI2 program. So these two projects are actually outside of that production capability that we talked about, that 55% production capability, but also looking forward, because you can see how things like this are really going to become part of our infrastructure. So, even closer to home here, thinking about Blue Waters, as Bill mentioned, ongoing and continuing discussions about the next generation of Blue Waters, and make no mistake about it, I'll talk about this a little bit later, and this came up in the National Academy report. There is, and it's absolutely recognized, that there's a need for a leadership class track 1 capability like this for science and engineering, and so those discussions are ongoing. So thinking about the future again, I wanted to bring in the issue of data, because I think everybody here, and again, this was something that came up in the National Academy report again and again, was the importance of data. So if you look at that middle layer, so down at the bottom, yes, we need the storage capabilities, but perhaps even more than that, yes, we've got this existing middleware now, but there will be, I believe, and I think many believe, a new set of data services that will evolve that have to do with accessing data, discovering data, being able to do analytics, to do question and answering, and sort of higher level functions on that data, as well as the underlying just access and discovery of that data. And then, of course, one needs to compute across that. So I think this notion of data is going to really pervade the whole stack that we see, all the way from the physical capabilities at the bottom to the kinds of science that people are doing, with some kind of new layer of infrastructure in the middle. And so I'm going to talk a little bit about one of the NSF big ideas on harnessing the data revolution, which sort of falls right in this sweet spot here. Okay? And then in the end, again, a bullet point, remembering that the reason that we're doing this is to enable and accelerate science. And this includes both just the science that goes on in all of the directorates, but also some of the signature programs like Understanding the Brain, innovations at the nexus of food, energy, and water systems, that's Infuse, Smart and Connected Communities, and the facilities, and those that are supported by the MREFC, sort of the large-scale infrastructure programs. I mean, more and more increasingly, all of this requires cyber infrastructure, and the foundation understands that we need a coherent reference model architecture and actually set of capabilities that can be provided across all of science and engineering here. Okay, just again looking forward, and then I'm gonna stop for a second and see if we want to have some conversation here. Bill Gropp is going to talk, I think, at dinner tomorrow. Is it the dinner time talk tomorrow? Yeah, about a really excellent report that came out just a couple of, maybe 2 months ago, and they just briefed the ACCI, the ACI Advisory Committee on this. You see the title there. They laid out 4 goals there and made 7 recommendations. I'm going to let Bill walk you through those. At a very high level, I just want to point out 2 of them, really talking about the leadership, right? The leadership that the United States must have in computational capabilities for science and engineering. And so the first is obviously to continue to grow, and I think grow even faster, the comprehensive, make investments in advanced computing, hardware and services, software and algorithms. So thank you, Bill, for echoing that we have this cyber infrastructure ecosystem. All of those are important so that to keep our researchers at the cutting edge of the frontiers. And you see some of the sub-bullets there, that research must come first, production capabilities are important, and to think about partnering with some of the other agencies. I had a conversation over breakfast about that. And recommendation 2, and then I'll stop here with the recommendations, because there are others, and Bill will go into more detail, but to support the full range of science requirements. So remember when we saw Blue Waters, we saw Stampede, we saw Comet. I was talking about how even from a computational standpoint, the set of needs is very broad, and that's what this is calling out here. integrating support for data-driven science. We just talked about that with that little green oval there. And something I mentioned earlier, providing and investing in one or more large, tightly coupled parallel computer systems for high-performance applications, like the ones that you folks are talking about here. So you should know that this National Academy study panel, which had noodled on this for actually a couple of years and thought deeply and talked to lots of people on this, really came forward with a very strong recommendation on this. Okay, so there are a couple things I'd like to talk about, but they have to do with the National Strategic Computing Initiative and also the NSF Big Ideas, and obviously cyber infrastructure is going to play a really important role in both of these here. But before I do that, I think I've been talking probably 20 minutes since Mike asked that last question, so I think I should stop. This is what I've tried to do here is give you sort of the broad view of cyber infrastructure broadly writ, and clearly, as a leadership class capability, Blue Waters is incredibly important. But we have this much larger ecosystem in which it's embedded, and again, as Bill and his committee has noted, and I've said it, that's not just the big iron, it's also about the software and the people and the networks and the data. So with that, let me any reactions or any comments? Yes.
Jim, maybe just a question. The way you presented the software stack,
The reference architecture.
the software, mostly the software stack,
Oh, okay.
APIs and so on, and the data discovery and leadership. These three, seem to be to a large extent separate. But moving forward, can you elaborate a little bit more on your view of how these three should come together in a more organic and more...
So those three things are leadership capability,
data
the data science piece.
And the software stacks, the APIs that make it easier for the science
Okay.
to be able to use
Okay.
this infrastructure.
So one May's comment was that those are sort of separate now, but how might they be integrating in the future? Let me say the first thing. Let me take the easy one, right? And that's the integration of data and computation. So as everybody here knows, data alone isn't going to do anything for you, right? So you have to compute over that. And so while I think there's a lot of open issues, and the community broadly is going to have to talk about roles and responsibilities for maintaining data. I mean, NSF does have data repositories, but so do the universities. How's that going to work out? But apart from sort of the data itself, when you want to do something with the data, to me, the data and the computation have to be incredibly closely coupled. And when you have to start thinking about that too, when you think about what are the egress costs of moving data from one place to another as opposed to moving computation there. So of course, this is something this community has thought about and the grid community has thought about for a long time. It's really going to come to the forefront in the next couple of years. And so I don't imagine there's any way we can move forward with data without thinking about computation at the same time. Okay. Now, in terms of the software that sits on top of that, so integrating that, so I take it as a given that those are already coupled, and that goes. I think that also goes for coupling the leadership class and making that more integrated with the other cyber infrastructure capabilities. Honestly, I don't know how that software is going to evolve. I don't know the degree to which different increasingly higher levels of abstraction can mask away the underlying computational paradigm. I mean, that's a tremendous challenge that this community faces, right? Do you really, what's the trade-off between doing something on something very tightly coupled and doing something much more on a loosely coupled, embarrassingly parallel, but also very cheap per core type of commodity infrastructure? And every now, so I had a long conversation with Bill about this at that ACCI meeting where we were talking about, well, I won't quote him because I might quote him out of context, so I shouldn't say that. But what we were talking about was there are absolutely certain algorithmic techniques and ways of solving problems that map so well onto this tightly coupled architecture. And the question is that absolutely mandatory, or are there other ways of thinking about that? And only time's going to tell, right? Whether how that how that actually shapes out. So I actually think that's an important research question that this community is going to be answering over time. I think another question is going to be sort of at a lower level when we have more heterogeneity in terms of what's happening on chips, that whether or not there'll be layers of software that can mask that, or whether we're going to actually have to be able to program deeply down and understand some of the embedded capabilities, next generation heterogeneous processing happening on the chips. So I don't know the answer to the software piece. I can tell you the data and the computation will obviously have to be tightly coupled. Yes?
So you had that plot of cycle utilization.
Right.
Different lines, and there were two slopes on that plot, right? 2005 to 2010, and then 2010 to 2015.
Yeah.
Explanation for the change in slope, and any sort of, and how's that going to change it?
Okay, so that's a great question. Let me put that up because that's a really good observation. The observation was when we were looking at these service units, sorry. Not quite sure what's happening here, except that it's not working. So I won't go back any further. But this had to do with when we were plotting exceed service units as a function of time. And the comment was made that there was sort of a slope where it was really increasing exponentially fast on a log scale already, and then something where it got flatter, where it's still increasing exponentially. And what are those two slopes? It's a really good question. I might ask Ed Seidel to comment on that. About what was actually happening in that first case where you saw that really quick ramp up. So now we see sort of the continuing increase. It's increasing at a different sort of with a different exponential constant, but still increasing exponentially. In a sense that it's partially self-limiting, right? I mean, there's only so many cycles or service units that are available, and supply does not equal demand. That's why we have a P-rack, and that's why we have an X-rack. Certainly the NSCI is calling for increasing that kind of investment so we can come closer to meeting, demand being met by supply. But I don't know. It's always a little embarrassing to. Well, okay, we've got somebody in the back who wants to comment on that.
At least in some areas of physics, part of that turnover is we're getting better. We've got algorithms that don't need as much for some of what we do, so we're making progress, realizing there's not as many cycles as we would want, so we've had to compute smarter.
Okay, so that's great, right? So the comments made that scientists are learning to compute smarter, and so we were just talking about the paid program earlier today that's aimed at doing exactly that. So, okay, so that's a great point. Yes?
That graph didn't include Blue Water's delivery.
That's right, that graph did not include Blue Water, so that was just the exceed service units. I'm trying to track something like that down, but for Blue Waters, we've just got the recent data on that. Yes?
So I guess just to make the point that if you look at the XRAC meetings, there's three different numbers that come out. There's the number
That's requested, right?
There's the number that the review board would like to give out.
Right.
And there's the number that's actually available.
Right.
And the gap between the number that the review board would like to give out and what's available has been growing over time. And I suggest that that's a large reason for that.
Right. Right, so there's increasing demand that's coming in. Then there's the allocation. Then there's sort of what's recommended, and then there's what's actually available there to be awarded. And Dan's comment is that gap has been increasing between those two, and that's really important. It's important to note that. So, point well taken. Okay, other comments? Going once? No? Okay. Oh, yes. Thank you.
So you talked about data having to be near the computing. Those of us who are working on Blue Waters have been told that if our allocations end, so will our access to the storage system there. So we can't afford really to leave all our data there while we're computing for 3 years. And we all have to have data management plans.
Right.
And the NSF doesn't always make it easy to rely long-term on any particular facility. In my career, I think I've been thrown off of 3 mass storage systems and had to spend time over weeks or a couple of months getting data off. a problem that ought to be solved.
Okay, so I couldn't agree with you more. Let me see if I can paraphrase that, right? So the real dilemma that we find ourselves in with data increasing like this, but I mean, it's been a problem all along, right? The data management plans say, you say, this is what I'm going to do with my data, right? But after you're to me, the real question is, what happens after you're funded? Because while you're being funded, there's going to be stuff that's going to be budgeted that will actually go into, I mean, you can budget costs for data management then. But after you're funded and your data's there, then to me the real question is what happens to that? We do have repositories, different disciplines within NSF have some repositories. I think the real question is how as a community are we going to decide what data that we want to be able to invest in having a longer term lifetime in a repository that's curated after the funding goes away for that particular project, right? And so one then has to start looking about the use of the data by other scientists, and I think it's going to be very difficult for every data, generated by every scientist ever funded by NSF to find a home in a repository long term. And I agree it's a problem that should be solved. Let me say that the constraints in solving that problem are in that budget graph that I showed you, right? And so I spent some time with the MPS Advisory Committee a few months ago talking to them about these kinds of issues, because if NSF makes investments in that, then under a flat or 1 or 2% a year budget scenario, that money is going to have to come out of other research and research activity expenditures, right? And so there's going to be a very delicate balance that has to be defined there. So I don't think I'm not answering your question. I'm just saying these are the constraints under which this problem has to be solved. And it's going to, so when I showed that reference architecture, and I had on the left-hand side governance going up, I think that's going to be incredibly important, because the scientific community has to be engaged in these discussions about how much investments we're going to be making in the preservation and curation of the data, and how much funding is actually going into the funding the new science going forward. And that trade-off it's a hard choice.
Perhaps we need panels, not individual investigators who decide what deserves to be preserved long term.
Absolutely. So the comment was made, we need panels rather than individuals to determine what's going to be saved long term. So that's absolutely true. And actually the repositories, especially like in the geosciences, right? Those are curated. They're not curated just by one individual, and in a sense, they represent and should represent a community consensus that here are some metrics that are going to indicate some measure of utility of data to the community that's being supported there, and those kinds of decisions have to be made, and there may have to be deaccessioning, right? So you're in a repository, but now you're not in a repository because of budget constraints. And so when I said governance, I didn't mean governance by one individual. I meant governance by the community, right? And it could be, it could take the form of a panel and something like decadal surveys or something like that astronomy does, or advisory committees that get together. What that structure ends up looking like, I don't know what that's going to be, but you're right. Okay, yes?
Just a quick question. There's many exciting things on the NSF agenda, and you've mentioned international collaborations a number of times, including CyberInfrastructure connectivity to Europe and Asia and so forth. And then you also mentioned exciting new science challenge that NSF wants to get behind with regard to Human Brain Project. And so I think, as you well know, the Europeans are engaged in this area for some time. So among these many exciting different things to go after, what is the way that NSF is thinking about prioritizing the international collaboration on?
Okay, so Bill's question had to do with Well, so there are so many exciting things. What is the priorities, but specifically with respect to international collaboration. And I can tell you, maybe the best way to think about it is you can look at where we're making the investments, and that will sort of help speak to priorities. So certainly, we're making some of the investments in the networking capabilities so that we have connectivity to the instruments used by scientists around the world. So absolutely there. NSF is one of the major funders for the Research Data Alliance, which is really trying to define, sort of to be for scientific research data, what the Internet Engineering Task Force was for the Internet. So a bottom-up grassroots activity to define metadata structures across different areas of science and engineering. And so we support RDA USA. There's an RDA activity going on in Europe. And we're having discussions with folks in Japan, and also an activity going on that's coordinated through this RDA funders group with folks in Europe also. And so that, I mean, again, when you think about it, metadata is almost sort of like networking, right? It's something that's so fundamental and so far down in that stack that you need investments in that if you're going to do any hope of collaborating there. So I would say those kinds of investments are the ones. And also we have a lot of individual research, collaborative research programs that go on within all of the directorates that allow researchers from the US to be funded with researchers from, collaboratively funded with researchers from other countries. So computational neuroscience, that's a joint program between NSF and CISE, the National Institutes of Health, France, Israel, and Germany, for example. So in some areas where there's a lot of community desire and push to do that, we have international research collaborations on the infrastructure side, mostly on networking and on the data side. Okay, so thank you for all the questions. So that was great. I'm going to move on and just I want to. Now I have to go through all my slides again. Here we go. Okay. So I want to, in the last 10 minutes here, touch briefly on the National Strategic Computing Initiative and NSF's big ideas. And I want to focus on the NSF big ideas a little bit more. So let me just tell you that I already mentioned that the National Strategic Computing Initiative was launched a little less than a year ago. It came sort of after the 2017 budget was more or less set. So the 2018 budget, I think from an NSF standpoint, is the first place we'll see some impact there. You see 5 objectives there. The first one's sort of the exascale activity, and honestly, DOE is taking a real lead on that. In the 3 middle ones shown in red, a technical synergy between platforms for modeling for the computational and data side of things. So that's exactly the comment that Wen-Mei mentioned earlier. Research to take scaling beyond current device limits, so that's different forms of sort of getting down into the hardware and thinking about new forms of computation, quantum, for example, there. And then finally, increasing the capability and capacity of the ecosystem, that's software, and people, if you start reading down into that. So let me not go through this. I'm hoping my slides will be available. My slides will be available so you can read more about this, and you can read. There will be an implementation report coming out, public implementation report coming out about this in the not too distant future. So again, objectives 2 and 4. This has to do with the data role, the fusion of modeling and simulation with the technology used for data analytic capabilities, and then finally this enduring national HPC ecosystem that I've been saying again and again and again, the workflow, the algorithms, the software, and the workforce there. Let me just say that within CISE, we have a program called CIF21, CyberInfrastructure Framework for 21st Century Science and Engineering. That has been a 5-year program. 2017 is the last year of that, and so we're ramping up. If you were to look at our 2017 budget submission, our CIF21 program morphs into an NSCI program and a program we call D4SDA, Data for Science Discovery and Action. And so those are the sort of the two, and we're collaborating with other directorates on those as in CIF21 going forward. So a lot of partnerships there within the foundation, and a path forward for the CIF21 activities. I'll skip that. Okay, big ideas. So how many people here saw or read about the NSF big ideas? Okay, wow, not enough. I was speaking to a bunch of computer scientists not too long ago, and I said, how many people had heard about the president's initiative on computer science for all? And I figured, wow, the president taking a weekly address to talk about computer science for all, everybody must have. And I was a little disheartened. But anyway, so I'm trying to spread the good news here. So at the last National Science Board meeting about a month ago, Franz Cordova, our NSF director, unveiled a set of NSF big ideas. And the idea here was to say, look, here are really important areas of science and engineering where NSF needs to be investing and can really, where you get really high marginal utility in the investments that you're making. And Jeffrey Mervis, the science writer, NSF director, unveils big ideas with an eye on the next president and Congress. So yes, I mean, certainly this is about going forward for science and engineering, but it's also about the next Congress and the fact that we will have another president a year from now. So here, there were 9 ideas that were put forward. 6 of these were research ideas and 3 were process ideas. And so let me just read to you and maybe just say a sentence or two about each of these research ideas, because I think what you'll see is that the kind of work that's going on here at the Blue Water Symposium cuts across every single one of those, okay? So harnessing data for 21st century science and engineering, right? So that's all about the data infrastructure that we were just talking about, that the NSCI calls for, the integration of data, both in terms of physical capabilities as well as in middleware and the integration of computation and data in that next generation of cyber infrastructure. And so that, and actually a continued evolution of the cyber infrastructure is a big piece there. There's fundamental science that has to be done. We had a joint MPS CISE workshop among mathematicians, statisticians, and computer scientists about what something like a math center might look like in data science. So there's fundamental science that needs to be done. In the math and the statistics and the computer science. There's fundamental science in the data part of that, and then there's also the fundamental underlying infrastructure that's needed there. Shaping the new human technology frontier, so that's a lot about how we as people are going to be seeing or engaging with computation. The way I like to say it is computation will be embedded around us, on us, and in us, and there'll be data from that, and so the smart and connected cities and communities activity sort of falls under this. So there's a lot of privacy issues there, there's a neuromorphic computing piece of that also in the back end in the cloud that will be important. Understanding the rules of life, this is being led by the Bio Directorate from genotype to phenotype, predicting phenotype. The quantum leap, so leading the next quantum revolution. I think it's probably fair to say the US is in some areas behind some of our European counterparts in thinking about quantum. Navigating the new Arctic, there's a lot of sensing, a lot of climate that goes there, again with a big computational piece. And then finally, Windows on the University era of multi-messenger astrophysics, which has a huge computational piece also. So I think that the kinds of things that we engage in and the research that we're hearing about here at the Blue Water Symposium really cuts across all 6 of those research ideas. Let me just say that in terms of process ideas, growing convergent research and NSF is one of them, and so that's think of even deeper collaboration than interdisciplinary, which again is a hallmark of what happens with a lot of cyber infrastructure. There's an ongoing discussion of using MREFC not just for large-scale facilities, but also for in the mid-scale, so something larger than MRI, but smaller than MREFC. And and Fleming Krim, the AD for NPS, have talked to the Science Board multiple times about this and about the different needs for cyber infrastructure for this kinds of mid-scale research infrastructure. And then NSF 2050 is a way of addressing these questions. So I'll leave my slide, again, my slides will be available, and this is just some more detail about a couple of these, harnessing the data revolution, the human technology frontier, and the quantum leap. So let me just summarize that it's great being a graduate student, right? I know I'm going to say old when I say this, right? But it's never as good as when you're a graduate student, right? But it's particularly exciting to be a graduate student when you're in an area where there is so much going on, and what you are doing is so central to what happens in so much of science and engineering. And so I really think it is an incredibly exciting time. It's impactful and important to be in computational science and computer science and ACI, that we see, from a ubiquity standpoint, we see it all around us. I mean, there are people from every directorate here, represented by NSF here. There's engagement across the broad scientific enterprise. And then finally, believe me, I hear this, there's an urgency, right? We've got to move forward. There are things that we have to do. And all those things combined make for it to be a really exciting time. Okay, so with that, I think I'll stop and say thank you. Thank you for all the questions. Thank you for the invitation to come here. Thank you for being here, for taking part in this symposium. Bill mentioned his thanks. And again, I want to thank Ed Walker and my colleagues at NSF for everything that they're doing for ACI. And I want to, again, thank the Blue Waters leadership team and all the folks working at Blue Waters for all they're doing for the science and engineering community in the country. So thank you very much.
So I think we have time for maybe one or two last questions if anybody has them.
Sure.
You talked about the National Strategic Computing Initiative, but a big part of the initiative is a big IRO. Now, of course, I realize it's a pregnant question, but there is some agencies have plans, at least well-articulated plans to create exascale. Various countries have very well-articulated plans. We represent here a particular subset of the community which may be interested in those. What can you tell us?
Sorry, what can I didn't, I'm not sure I got the whole question. Let me see if I can repeat it back to you and see if I got it quite right. So this is about the National Strategic Computing Initiative. Remember, there are 5 pieces to that, right? The first part is the capable exascale, right? And then the second part is the integrated data with computation. The third part is on beyond Moore's law, and the fourth part is software, people. I think your comment was that some agencies, and you're probably talking about DOE, but I don't know. But there are some agencies that are really moving very forward, that are moving aggressively forward on meeting that first one. NSF's sweet spot, I think, and Irene and Ed might want to comment on this also, I think is really on the second, third, and fourth. So there's some basic research. I skipped over what we were doing in the XPS program and some of the stuff that was some of the hardware, more hardware-oriented research going on that could contribute to the exascale piece. But I think our sweet spot for us as a foundation is really on the second, the data analytic, combination of data analytic and computation, the on beyond Moore's law from a research standpoint, and the software, people piece. And what are we doing there? Well, so I mentioned, was your question, what are we doing there? Okay, I thought that might be it. Again, when this was announced last year, our budget had already been submitted for 6 months. But we did sort of know the shape. We didn't actually know exactly when this was coming out. But we had already identified NSCI as something that we, CISE, MPS, GEO, we're starting to invest in and move some of the investments and adding some investments in the case of CISE over what we were doing in CIF 21, CyberInfrastructure for the 21st century, and move that into NSCI and D4SDA. So we did that even with a limited, budget, right? We started moving resources there. We don't have, so again, the budget for CISE is a little under $1 billion. So we can't easily move around hundreds of millions of dollars. Even tens of millions starts to when they start adding up is difficult. So we don't have the flexibility with flat funding to move really large sums of money around. And so again, the hope will be that there'll be additional investment coming into NSCI. I think we've set the foundation for that. We've made some investments in that ahead of the curve. And I guess all I can say is, this is supposed to be a 10 to 15 year initiative. So for us at NSF, we have to be looking at the 2018 budget and beyond. Okay.
I think it's indeed exciting to hear which will bring us to exascale, I suppose. My question is, does NSF has a timeline for when that would happen?
The question was, does NSF have a timeline when exascale will happen?
100x
Oh,
capability.
I don't think we yet have a good feeling for when that's going to be happening. I mean, maybe one thing I might defer to Bill on this, but one of the things that also came out of the National Academy study was for a question. I mean, it's a great question, right? And the NSF need to be a little bit more proactive in publishing roadmaps. I don't think the roadmaps can be quite as detailed as some of the roadmaps that are coming out of the DOE in terms of where they see their technologies going and this many machines with this many nodes and things like that with these kinds of capabilities. But we do need to do a better job in sort of publishing a sort of in the future where we see things going. I think one of the first steps will be to understand where the science really wants to go also. So there's both the capabilities in terms of the infrastructure, but there's also what is it that the science is demanding, right? Because we don't want to go somewhere just to go faster, right? We need to know that this is something that the science community really needs. And when we start thinking for the science community more broadly writ, we start thinking about the early days of exascale, whenever that's going to happen, maybe NSF and DOE, and this is another report, another recommendation that came out of the National Academy report is to work together a little bit more closely with, to leverage each other's capabilities. So I think I can say to you, we will be focusing a lot more on roadmaps than we had in the past, but we don't have that roadmap right now. Yes. Last question, Bill?
More for you, but yeah, pretty.
Well, I'm willing to stay here as long as you want to stay here. But we do have a break, and I'll be hanging around for the break so we can continue the discussion. So last question.
Taking advantage of your 32 years as a professor, do you have any advice for people that are trying to move undergraduate computer science beyond single processor, games and animations, Raspberry Pi, to multi-core, many-core, what's needed to really get a community engaged?
So great question. Since you're all the way in the back, I'm assuming everybody heard it. There's a group, the IEEE TPDS. What does that stand for? IPDPS. Right, so I know Sudeep and Chip Weems are both involved with that. I will tell you, so I was involved in the networking, so IEEE and ACM every 10 years come out with their roadmaps of, I think it was in 2013, 2014 when the last one came out. And I will tell you, in the networking community, we were not engaged in that, and so we sort of panicked at the last minute and said, look, we the networking community need to have input into this. And so we had a workshop, and in the end it worked out okay. I will tell you that IPDP, well, that's the conference, but there's a group of people who have been working with both the ACM and the IEEE on that. I will tell you as an outsider, I thought that community was better organized than any other community, at least with respect to undergraduate education and what curricular recommendations might look like, than any other community that I saw. So my sense is that you folks are doing a good job. I can tell you that there are ongoing discussions, and this ties into computer science for all, right? So computer science for all is really aimed at the high school. There's a new computer science principles course. Okay, right, the Technical Committee on Parallel Processing, and maybe, is that the group that sponsors IPDPS? Yeah, okay, great, right. So it's that group. I know that group is actually in discussions with folks in CISE about actually infusing that into this computer science principles course. So computer science principles is a new AP course, which means it's also taught at the college level. It's meant to be a broad introduction to computing. It's not about, there's programming in it, but it's not about programming. And they want to do, so CSP has a bunch of principles, but you can instantiate that different ways. And that group has been talking with the folks in computer science principles about an instantiation of CSP that has a lot of the parallel and distributed systems sort of infused into that. And so if you send me an email, I can put you in touch with those, who those people are, because we've been having those kinds of discussions. I think focusing early in the pipeline is an incredibly important thing. Changing undergraduate curricula is incredibly hard, right? Because it's in the individual hands of you and you and you and you and me and what we choose to teach. Even our department chairs can't tell us what to teach, right? I know that as a department chair. You're going to put your own spin on it, and that's the way it should be, right? So the question is, how does this community, and this is true about computational science, I think more broadly writ, how do you infuse that into an undergraduate curriculum in a scalable way? And let me say what I mean by scalable, and then I promise I'll stop. When we're talking about CSP and how to get computer science beyond programming in Java into high schools, the way we were able to do that scalably is to work with the College Board and develop a new AP exam, the community develop a new AP exam on computer science principles. What does that do, right? In Massachusetts, there's 130 different school districts. If I want to get computer science into just Massachusetts high schools, nobody has enough time to visit all 130. But if you do it by getting the College Board to adopt it, then what happens is the College Board will pull the schools into wanting to do it. And I think we need some kind of mechanism like that. Obviously, we don't do advanced placement tests, but we need a scalable mechanism to introduce things like computational science, like cyber security, sort of more broadly into the undergraduate curriculum in computer science. I don't know how to do that. We have just funded a National Academy study that's starting up to look at both the growth in undergraduate majors in computer science, but also to partially address this question. So thank you. And I'm sorry for overstaying my welcome a little bit.
We appreciate everything. So let's thank Jim again.
Thank you.